Right, sir. So, okay, sir. So, before we invite today's speaker, Dr. Sudheer Kumar Tiwari, I'd like to pay a small homage to our late Professor Peter Molnar, uh, who breathed his last day before yesterday. So, means on the behalf of the Structural Geology and Tectonics Group of India, we sadly mourn the demise of Professor Peter Molnar. Just to give you a brief account of his contribution, Professor Molnar was born on 25th of August 1943 in Pittsburgh, Pennsylvania, and he received a Bachelor of Arts degree in physics from Oberlin College in 1965, and subsequently he did his PhD in seismology from Columbia University in 1970. Then he actually worked on the evolution of mountain belts, particularly the deformation of continents and structure of the evolution of the mountain ranges. And he has been a prolific teacher as well as a great researcher, as we all know. And he also won the Crawford Prize from the Royal Swedish Academy of Sciences in 2014 for his groundbreaking contribution to the understanding of global tectonics, in particular the deformation of continents and the structure and evolution of mountain ranges, as well as the impact of tectonic processes on ocean atmosphere circulation and climate. And he was also a life fellow of the American Geophysical Union and Geological Society of America. Professor Peter Halle Morner, at the age of 78, breathed his last in Colorado this Thursday, June 23rd, and may the Almighty give strength to his near and dear ones to bear this loss. So, in taking into account his contribution, I'd like to request all the members of our group to maintain a 1 minute silence to mourn the demise of Professor Peter Molnar. Thank you all. May his soul rest in peace. Now, with the permission of the chair and as your host for today's evening, I'd like to welcome Dr. Sudheer Kumar Tiwari to deliver the monthly lecture of this month, organized under the aegis of Structural Geology and Tectonic Studies Group in association with Department of Geology, Banaras Hindu University. Welcome, Dr. Tiwari. And before I hand over the stage to Dr. Tiwari, I would like to provide a brief introduction about today's speaker. Dr. Sudhir earned his BSc and MSc in 2011 and 2013 respectively from Allahabad University, Prayagraj. Subsequently, he qualified NET and GATE examinations and joined IIT Bombay. Dr. Tiwari completed his PhD from IIT Bombay in 2019 under the able mentorship of Professor Tapas Kumar Biswal. During his PhD, Dr. Sudhir worked on the deformation and technothermal history of Ambaji Granulite, Southern Delhi terrain, Aravalli, Delhi Mobile Belt. Currently, Dr. Sudheer Tiwari is an assistant professor in the Department of Earth Sciences, IIT Roorkee, since 2020. Dr. Tiwari has published around 8 research articles in journals of international and national repute, like Journal of Structural Geology, Tectonics, Lithosphere, JS, and others, and several other papers and abstracts in national symposiums and workshops. His main research interests lie in large-scale tectonics and structural geology, So now I would like to request Dr. Tiwari to present his talk on the implication of dynamic recrystallization mechanism for the exhumation of lower crustal rocks, a case study from the shear zones in the Ambaji granulite, northwestern India. Dr. Tiwari, please.
Thank you, Dr. Sandeep and RDS team for inviting me. I am honored to be here. Now I will start presenting my topic. Just 1 minute. Are the slides visible?
Yeah, Sudheer. Yeah.
Okay, thank you. So today
You can go to the presentation mode.
Yeah, I have. Is it in presentation mode or not?
Right now, it is not.
Okay, I will again share my slide. Just 1 minute.
You can share the entire screen, then you can select the PPT.
Now?
No, not yet. Actually, your
Just
is not in presentation mode. It is in slide mode only. Now you can click the button for slideshow. If you are going to share, don't share your tab. You share your entire screen.
Share your entire screen and then go to the slide mode.
Now is it visible?
Yeah. Please.
Okay.
You can hide the bottom bar. Yeah. Over there.
Now is it visible?
Yeah. Please go ahead.
Okay, thank you. Thank you very much. So today I will be presenting I will be talking about implication of dynamic recrystallization mechanism for the exhumation of lower crustal rocks, and these particular studies has been done in the shear zones of Ambaji granulites, northwest India. So these are the outlines of my presentation. First, I will introduce my research area, then what is the research gap and what motivates to choose this particular topic, and what are the objectives of the present study, then methodology and result, then finally conclusion and summary. So our particular research area, Ambaji granulite, belongs to the southwestern part of South Delhi terrain, which is a part of Arauli Delhi mobile belt. So this one is my study area, which comprises different granulite with different sets of granites, which included these granulites, and which are later cross-cutted by different ductile as well as brittle shear zones. So in this particular lithological map, you can see that these particular blue color rocks are pelletic granulite, and these are calcareous granulite, and there are also we have mafic granulite here, mafic granulites. So these three granulites are present in the particular study area, Ambaji granulites, and there are four phases of granites which include this particular area. G0 granite, which is around 960 million year old, G1 granite 860 million year old, G2 granite which is around 840 million year old, and G3 granites around which is last phase of granitic intrusion in this particular area. It is around 759 million year old. So I will be talking about these particular shear zones, which ductile shear zones, which are just 1 minute. This particular shear zone, which are cross-cutting these granulitic terrain. So these particular shear zone form during D2 deformation. So particular area, this particular area, we have seen what are the particular lithologies. Now we comes to the deformation phases in this particular area. So there are 4 phases of deformation which Ambaji granulite has suffered. So there is D1 deformation, during which our granulitic metamorphism happen in this particular area. During D2 deformation, D1 deformation is around 860 million year, and during D2 deformation.
So I'm interrupting just a minute, just to make myself clear.
Yes,
This
sir.
shear zone means that pink color. So is it this on the left? Where your pointer is.
These are shear zones.
S-shaped shear zone. I mean, the shear zone itself is carved
Yeah,
like that.
rotated. This has been rotated due to F3 folding. I am coming to that particular point.
Okay.
I will be discussing all these things, how lithologies has been rotated due to folding, large scale folding. So in this area, sir, I will come to that point. Let me explain what are the major deformation phases. Then I will explain fold and all
Yes,
these.
please go.
Okay. So in this particular here, these granulites are formed during D1 D1 deformation, which is around 860 million year, and these particular shear zone has been formed during D2 deformation. D2 deformation. So during D1 deformation, F1 folding happens, and G1 granite intrusion also happens simultaneously, and metamorphism happens. And during D2 deformation, our F2 fold forms in that particular area, and G2 granite intrusion, as well as simultaneously the G2 granite has been sheared along these shear planes, and through these particular shear zone, as we all know that shear zone acts as a pathway to exhume lower crustal rocks. So along these shear zones, our granulites has been exhumed from 25 kilometer to up to brittle ductile transition zone, suppose 15-16 kilometer. Then after that, these has been exhumed to the surface. Thereafter D2 deformation, in D3 deformation, there is F3 folding and G3 granite intrusion. And during D4 deformation, there are brittle, normal, and strike slip faults, which during normal faulting, these cover rocks has been removed and collapsed. So these particular granulites are on surface now, which basically forms at 25 kilometer depth. So there are 3 phases of folding, as we discussed during D1, D2, D3 deformation phases. So there are F1, F2, and F3 phases of folding in this particular area. So our F1 and F2 are coaxial, and F1 is recumbent in nature, showing your northeast and southwest trending F1 and F2 axial plane, and F2 folds are upright to open kind of folds, which also show northeast to southwest trending axial planes. And here F3 folds in this particular area shows northwest southeast upright kind of folding. So we can see that F1, F2 are basically coaxial, showing northeast southwest trend type of fold, showing northeast southwest trending axial planes, and F3 is showing northwest southeast trending axial plane, and due to these different deformation mechanism and folding event, we will get different type of interference pattern in that particular area, but we are not going to discuss all those things. We will mainly focus on this shear zone, and mainly on the recrystallization mechanism process in this particular shear zone, how these particular recrystallization mechanism which we identified in this particular high grade and low grade shear zones. So here we can see there are two there are two different type of shearing event happens, like when the material which forms at 25 kilometer is exhumed along shear zone. At that particular point, we have high temperature shear zones. As in time it progresses, as it reaches around brittle ductile shear zone, it is over around 15-16 kilometer. It is around overprinted by mainly low temperature like Green's phase kind of temperature of shearing happened in that particular area. So yeah, I have also done structural mapping of that particular area. So here I have plotted the S1 pole and we have contoured that particular pole here, and after contouring we have plotted beta axis here, and these are the F1 fold axis plus intersection lineation. So the beta axis of these S1 contours will show the fold axis of your F2 large scale F2 large scale F2 fold axis. So here F1 fold axis, which we have earlier plotted, and F2 fold axis, both are coinciding. So from the field also we are showing that with the help of structural data, yeah, F1 and F2 are coaxial in nature, but F1 is recumbent and F2 is upright in type of folding. So we have also plotted the myelonitic foliation and stretching lineation present in that particular area. So most of the myelonitic foliation, these are myelonitic foliation, and SL means stretching lineation. So most of the myelonitic foliation are showing that these are these are dipping towards southwest direction, and most of the stretching lineations are showing these are moderately to subhorizontal to moderately plunging in south-southeast direction. And this particular whole Ambaji granulite terrain has 3 sets of brittle fractures and faults. We can see that north-south and around northeast, southwest, and around our east-west, around east-west, you can say. So these are the major brittle fractures. And one more thing, you can see that most of the protoliths in this particular area are elongated in northwest, southeast direction. And in this particular area, most of the protoliths are aligned in this northeast, southwest area, because these particular areas are affected by large scale F2 folding, and these areas are affected by a large scale F3 folding. That's why they have rotated these litho units in these particular directions in this particular area. So basically what motivates me to do this kind of work, there are in the particular collisional erosions, we see there are lots of high grade rocks now exposed on the surface. So these particular rocks, how these particular rocks exposed on the surface, there should be a mechanism. So these particular rocks are exhumed through shear zone, with the help of shear zone, because shear zones are excellent channels for the exhumation of these particular lower crustal rocks to the we can say up to brittle ductile shear zone. After brittle ductile shear zone, so normal faulting and those brittle fracturing will further reduce the cover material and will exhume it to the surface. So in this study, in this particular study, we will be talking about the exhumation of these material up to brittle ductile transition zone. So in this particular brittle ductile transition zone, we have a different dynamically recrystallization mechanism for quartz for different temperature and for different temperature pressure according to that particular depth through which these particular material were exhuming along these particular shear zones. So this study will throw light on several other globally less understood exhumation of deeper crustal rocks like granulites and all those lower crustal rocks, how they have been exhumed, how the material have been flowed, and during exhumation, how this particular dynamic recrystallization mechanism assisted in the exhumation process. So we will see all this. We will solve all these things in our study. So, what was the objective? Detailed study of field microstructure and petrographic and differential flow stress calculation, how during exhumation our differential flow stress have changed, and strain rate analysis, and unifying all above to better understand the exhumation process of these lower crustal rocks. So for this particular study, we have we have done field work and prepared thin section. And what kind of thin section? We have prepared XZ plane of strain ellipsoid kind of thin section, which we took oriented sample from the field and we cut along the lineation and perpendicular to foliation. So by cutting that particular oriented sample in this manner, we will get maximum stretching ellipsoid cross section, that is XZ plane of strain ellipsoid or that particular thin section. So in this XZ plane, we will get maximum deformation whatever happened in that particular myelonites. So we have done microstructural and petrographic study on these XZ section, then temperature range calculation from grain size analysis of those particular dynamically recrystallized quartz, then differential flow stress and strain calculation we have done. So for that particular thing, we have chosen quartz dynamically recrystallized grain, because quartz is common in high grade as well as low grade these particular shear zones. So for that we have for the differential stress calculation we have applied the formula sigma is equal to bdk power minus p with after Stipan Tulis 2003, where B and P are experimentally derived constant, and we have also multiplied this equation by 0.73 for the Griggs-Apartus correction, and we have then used these particular paleopiezometer calculations in the strain rate analysis. So strain rate analysis is done by epsilon dot is equal to x sigma power n exponential minus q by rt, and this formula is given by Patterson et al. We have applied these two formulas to understand how the differential flow stress as well as strain rate varies during exhumation of these particular lower crustal rocks. So in my study area, these are field photographs. You can see various type of microstructures like here you can see some delta type of porphyroclast, some sigma type of porphyroclast. These are low grade myelonitic rocks from Ambaji granulite, and these are showing northwest sinistral sense of shear in northwest direction, and these are high grade myelonites which I am talking about. So in this you can see the feldspar behaves in a brittle manner, and these are surrounded by basically biotite and quartz. This will be more clear in thin sections, And here you can see stressed feldspar grains in high temperature shear zones. So during high temperature shearing, what happens? We have these particular minerals when your temperature is greater than 500 suppose degrees Celsius. So your feldspar, quartz, biotite all will behave in a ductile manner, where in this particular case your feldspar will behave as a brittle manner when temperature is around 350, suppose 350 degrees Celsius. Feldspar will behave in a ductile manner, and quartz and biotite will behave in a ductile manner, and feldspar will behave in a brittle manner. This will act as a solid object which will rotate in ductilely flowing matrix like that. And in this case, what will be our brittle minerals which will behave brittle manners? In this case, our garnets will behave like in a brittle fashion, and all these that will act as a rigid class which will be rotating into this ductilely deforming matrix. So this high grade myelonites or high temperature myelonites are showing top to northwest thrust shearing. So again, these are low grade myelonites which are showing horizontal to subhorizontal stretching lineations, and these are high grade myelonites which are showing vertical in a thrust component sense, vertical stretching lineations. So these from the field itself, these shows that these are low temperature myelonites are behaving as a sinistral strike slip kind of shear zone, and high temperature myelonites are behaving as a top to northwest going thrust shear plane. So high temperature myelonites, during high temperature myelonitization, our material has flows vertically along these particular thrust, and during low temperature myelonites, our material has flowed laterally along this particular strike slip ductile shearing. Also, I have shown these particular sample locations in this particular map. I have collected these samples from every shear zone, starting from Balaram shear zone to Kuchitraseni, Balaram shear zone to Surpagla Kengora shear zone. So I will be discussing about the microstructure in terms of dynamically recrystallized microstructures of quartz, as well as different high temperature and low temperature characteristics, deformation characteristics associated with these high temperature as well as low temperature myelonites, which we have collected samples from the field. So one more thing to be clear, that these particular high grade myelonites are preserved at very few places. Mostly these are overprinted by low grade myelonites, that is green cyst green cyst species kind of myelonites. So at few places only we are getting these high grade temperature myelonites, which are showing thrust slip shearing, and the low temperature myelonites from the field itself, field as well as microscope, we have seen that these are showing strike slip sense of shearing. So our BL1 and BL2, these have been collected from Balaram shear zone, and BL2 is dominated by SGR type of recrystallization, which are overprinted at some places by BLG recrystallization, and BL2 is showing high temperature characteristic of high temperature deformation myelonitization, and it is dominated by grain boundary migration, as you can see. So these are showing high temperature myelonites which are formed at temperature more than 550 degrees Celsius. So we have also some deformation textures which are associated with this high temperature deformation. Chessboard twinning is characteristic of high temperature deformation, which is also found in this particular BL2 myelonitic section. So next one is PG1. We have next PG1 and PG2 from shear zone. PG1 AJ1 from our ASZ1 shear zone. So PG1 shows mainly grain shape preferred orientation with dominantly SGR type of recrystallization, which are again overprinted by BLG at few places. So again, AJ1, which is from SZ1 shear zone, is dominated by SGR type of recrystallization. At few places, it is again due to a retrogression, it is again overprinted by BLG, and AJ1 is also dominated by SGR type of dynamically recrystallization. And through this SPO, we can see that this is showing SC fabric, which is also showing sinistral shearing towards northwest. So again we have SR1 and SR2 type of dynamically SR1 and SR2 from SR1 and SR2, just one. SR1 and SR2 from SZ2 shear zone, and SR1 and SR2 from SZ2 shear zone, and these are also showing SGR recrystallization. With SGR recrystallization means subgrain rotation recrystallization with shape preferred orientation fabric, which are defined by also defined by biotype, which are marking the which are marking the C fabric, and these are marking the S fabric in this particular thin section. And SR2 shows the transition between, you can see that here SGR, and here we are getting GBM. So our SR2 shows transition between SGR subgrain rotation to grain boundary migration type of dynamic recrystallization mechanism in thin section. So again we have SR2, which shows SGR as well as GBM. So GBM means high temperature towards, it tends towards the high temperature myelonitization. So high temperature myelonitization, what are other microstructural characteristics? We have found deformation twill namely in plagioclase, as well as myrmecite intergrowth in this particular SR2 high temperature myelonitization, which are showing transition between SGR to GBM through dynamically recrystallization mechanism. So this also support that, yeah, this belongs to high temperature kind of deformation mechanism, which are preserved at that particular place during exhumation. So we have next GS3 and GS4. These are from SZ3 shear zone. So GS3 and GS3 is basically showing a SCR type of recrystallization with which is again overprinted by BLG at some places. And here we have biotites are marking C plane of this particular shear zone, and oblique grain shape foliation are marked by S plane. So again, GS4 is dominated by SGR type of recrystallization, as you can see. So next is our K1 and K2, which belongs to our last shear zone, which is your Surpagla Kengora shear zone. So Surpagla Kengora shear zone, we have K1 and K2. So K1 shows the quartz grain dominantly display GBM recrystallization, at some places which are just overprinted by SGR recrystallization, and K2 is dominated by SGR, basically SGR type of recrystallization. these are the thin section evidences, thin section and petrographic evidences of high and low temperature, as well as dynamically recrystallization mechanism of these particular myelocyte, high grade and low grade myelocytes. I have also validated these things with the help of at which temperature, what temperature this particular grain size are deformation temperature will slow. So our dynamic recrystallization are present in that particular area through grain size analysis. And for grain size analysis, we have done that particular thing with the help of ImageJ software. So with the help of ImageJ software, we have calculated D for each slide. We have taken average of D, matlab dynamically recrystallized grain size diameter for each sample. So that particular each sample has been plotted in this particular diagram, likely range of deformation temperature diagrams, which was given by Stipp et al. 2002. And when I have plotted our particular grain sizes, which we measured with the help of ImageJ, we found that this PG1 and GS3 are showing BLG, SGR transition type of recrystallization zone, in a transition zone type of recrystallization, and BL1, AJ, AJ1, SR1, GS4, K2, all these shows ESGR type of recrystallization, which we also have seen in thin sections. So, and ESR2 and K1 are in between SGR and GBM transition zone, and BL2 shows dominantly GBM type of recrystallization, which matches with our petrographic observations. So these are the results, all results which we have calculated. So for Balaram shear zone, we have BL1, BL2. BL1 shows SGR type of recrystallization, and BL2 GBM type of recrystallization, and differential flow stress varies from 12 to 18 approx. And number of grains, minimum number of grains we have taken 251 and maximum around 481 for each slide. These are number of grains which we have analyzed with the help of ImageJ for each slides. So we have calculated this grain size with the help of ImageJ, and this likely range of deformation temperature with the graph, the particular graph of Stipp and Tullis 2003. So and also this differential flow stress sigma is equal to BDK power minus P, where this particular D has been utilized for the calculation of sigma. So we have here differential flow stress for each shear zone, and we have strain analysis that we have talked, accounting all these temperature as well as this differential flow stress. We have calculated that strain rate analysis of silent dot is equal to that particular formula. This particular formula, A sigma P power n exponential minus Q by RT, where sigma we have obtained this particular from here. So and these particular things are showing that all of shear zones, the strain rates vary between around 1.20 into 10 power minus 12 to 7.26 into 10 power minus 16 per second, which is comparable with other natural shear zones around the world. So like that, this shear zone, in for all shear zone, I have calculated this grain size analysis, and with the help of grain size analysis, we have calculated differential flow stress, and as well as strain rate and likely range of deformation temperatures, which has been suffered during the exhumation of lower crustal rocks in those myelonitic which is presently observed in those myelonitic rocks which are preserved in the Ambaji granulite terrain. So same PG1 for SZ1, PG1 the dominant recrystallization mechanism is BLG SGR transition, BLG SGR, and for AJ and AJ1 SGR type of dynamically recrystallization mechanism, and for SZ2 we have SGR to GVM type of dynamic recrystallization mechanism, which are present in SZ second shear zone. And for SZ3 shear zone, we have two samples, GS3 and GS4. GS3 is showing bulging to subgrain rotation transition type of dynamically recrystallization, recrystallized quartz in those low-grade myelonites, and we also have SGR type of recrystallization in those low-grade myelonites. And for SKSZ, we have two samples, K1 and K2. K1 is showing from moderate to high temperature, it is transitioning between subgrain rotation to grain boundary migration, and for K2, it is showing SGR type of dynamically recrystallization mechanism. So we have plotted these stress and grain size, and all these are showing that these are showing a reverse kind of correlation. At higher grain size, we have lower differential stress, and at lower grain size, we have higher differential flow stress during ductile deformation. And we have also plotted this temperature and stress map. So in this, these red colors basically represent the high temperature kind of dynamically recrystallized mechanism, as well as high temperature myelonites which are preserved in the steady area. So most of our samples are overprinted by low temperature myelonites kind of things, and there are very few samples which are showing high temperature, which are preserved at few places, means high temperature type of dynamic recrystallization mechanism or features like grain boundary migration, SGR, GVM type of dynamic recrystallization, or chessboard twinning, myrmekite. All these are present in these high grade of high grade of myelonites in that particular area. So here next one is stress versus depth. Just one. Stress versus depth plot. So we have converted those temperatures into depth at the rate of 25 degrees Celsius per kilometer. Through that, we have plotted that, yeah, these are high temperature samples, and these are low temperature samples, and these are ductile curves, ductile creep curves, which we have plotted with strain rates and temperature. And these are normal thrust, normal strike slip and thrusting for brittle fracture for different tectonic regimes. So as the from here we can see that as we have converted those temperatures into depth, we see that it is that particular lower crustal rock is exhuming along this particular, at least what is preserved in that Ambaji granulite, it is showing 22 kilometers. So it is showing that from around 22 kilometers, these lower crustal rock have been exhumed, and they have been exhuming up in the vertical direction up to this particular B point from C and D. It has converted into through strike slip in strike slip kind of mode, because in vertical direction it cannot travel further, because around brittle ductile transition zone around 15 kilometer, when it is these particular curves are for ductile deformation. we plot thrusting for this particular brittle regime. So our differential stress needed for that material to flow vertically in that particular regime, brittle ductile regime, is around 230 MPa. So that's why here the material has been switched this particular vertical movement into horizontal movement in these particular ductile regimes. So this is the kind of tectonic model I have came with after correlating field, thin section, as well as petrographic evidences. So at high temperature, what we are observing that we have in field we have vertical lineation, and in thin sections these dynamically recrystallized quartz are showing GBM type of recrystallization. And as your temperature decreases, the dynamically as the material flows vertically, the temperature decreases, and the this will change the dynamical recrystallization mechanism in these particular shear zones, particularly in quartz. So around the BTT zone, like brittle ductile transition zone, these particular vertical flow of material has been like thrusting has been converted, our material has been slightly turned from vertical flow to lateral flow. So most of the thing our this lower crustal rock or granulite has been exhumed through these thrust faults, high grade along high grade myelonetic shear zones, and later it is overprinted by our lateral flow of strike slip or low temperature myelonites in that particular area. So this is the summary of this particular study. Most shear zone in that Ambaji granulites are low grade shear zone. At few places we get high grade shear zone, and these low grade shear zone shows a northwest sinistral sense of shear. The microstructural study of myelonites indicate that high temperature thrust slip shearing with GBM with vertical flow is preserved at few places. In most part, the rock has been extensively overprinted by low temperature strike slip shearing characterized by BLG SGR recrystallization with lateral flow. And temperature, and one more thing, this lateral flow did not account for exhumation of granulites, but it accommodated more of the strain in that particular area during this particular lateral flow. So the temperature range from 490 to 600 degrees Celsius for high temperature, and 390 to 490 for low temperature myelonites, and the differential flow stress for high temperature was 12 to 15 MPa, and for low temperature it is around 18 to 26 MPa. For high and low temperature shearing are myelonites which are preserved in Ambaji granulites. And deformation occurred by climb assisted dislocation creep, and strain rate was between 1.20 into 10 power minus 12 to 7.26 into 10 power minus 14 per second, like we observed in other natural shear zones around the world. So it is in one line we can see that these first our granulite has been accommodated through these high temperature showing approx vertical the stretching lineation exhumed through this first part, and later this has been overprinted by lateral flow of material with our SGR BGM and SGR BGM type of dynamically recrystallized quartz. So with field petrography as well as these dynamically recrystallization mechanism of quartz. We try to integrate all these things. So so by unifying all these things, we get that in that particular area, those lower crustal rocks, first they have moved in vertical direction through top to northwest thrust, and these are assisted by GVM type of dynamic recrystallization. And in later part, these has been overprinted by northwest sinistral strike slip shearing, which are assisted by bulging and SGR type of recrystallization flow. So that's all. This is the paper which is published with the help of this study. So thank you everyone, and I would like to invite everyone for questions and suggestion for future research in this direction.
Thank you, Sudhir, for your detailed talk. Now the session is open for discussion. Yeah, Dr. Pushpandu Shah has raised his hand. Please go ahead, Pushpandu.
Hello.
Hello.
Yeah. So in your shear zone, you have both recrystallized quartz and feldspar, right?
Yeah.
Yes. So why don't you use feldspar piezometer to calculate flow stress? Because you have both the phases now.
We have both the phases, but for most of homogeneity purpose, and our crust is represented dominantly by the rheology. Our strength of crust is dominantly represented by quartz. That's why I have chosen quartz for these calculation, differential flow stress, strain rate, and all these things, because in that quartz dynamically in quartz we can get from high temperature to low temperature but through feldspar piezometry we can get the values of only high temperature myelonites. That's why I have chosen.
The thing is, if I apply feldspar piezometer, will we get the same flow stress in the system?
I haven't tried, but I think that should be the same for high temperature part.
Okay, I'm not sure, because people are using now the people are using both quartz feldspar piezometer to quantify flow stress, because recently one paper came out by Speciale et al. In JSG. So they use quartz feldspar piezometer to characterize the flow stress in myelonite. So my question is, if I introduce this or if I calculate the flow stress from feldspar piezometer, will the value of flow stress be same as you are getting in?
It should be same as because at the same time during high temperature dynamic recrystallization, we get both quartz as well as feldspar, both are deforming in a ductile manner. So it should give approx same value of paleopiezometry, because we will be taking from the samples from the same depth.
No, the thing is, you are using the equation of Stephen Tallis 2003. Okay, yeah. So they performed experiment in quartzite at the temperature ranging from 800 degrees centigrade to 1100 degrees centigrade, right? Okay, so and you are using this equation to calculate the flow stress, right? Okay. So why not we are using the feldspar piezometer?
Feldspar,
Because it has been done by
yeah, it has no.
post-Cantalis. Yeah.
Yeah, also people are using EVSD for these grain size and paleopiezometer nowadays. But since the grain size were larger, around 75 to 118 micrometers, so I have used this particular manual grain size analysis with the help of ImageJ. And the limitation of this particular study is that in this type of calculation, we get minimum differential flow stress or minimum paleopiezometry of that particular place. But for that feldspar paleopiezometry, I haven't used it. I will try to accommodate that kind of a study in my next research. So,
Okay. 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 Thank you.
Dr.
Thank you.
Vikramaditya Singh, please go ahead.
Thank you.
hello.
So, hello, Tiwari. First of all, I would like to thank Dr. Tiwari for sharing such information in a simple way. Okay, my query is very simple. That one of photographs you are showing the myrmecite, right?
Yeah.
Myrmecite. So normally myrmecite is also observed in the granite rock that does not deform. So how we can differentiate these myrmecites, means myrmecites from the deform myrmecite due to the deformation?
I am showing myrmecite for the reason because it forms at high temperature. So the purpose of showing those myrmecites that these has been exhumed from high temperature deformation zones.
So is there any structure evidence for that? Can the evidence like the structures in terms of structure?
We are basically associating those high temperature deformation petrographic chessboard twinning and all those things with the microstructural dynamically recrystallized mechanism, that these particular dynamically recrystallization mechanism happened suppose greater than 500 degrees Celsius. So we are correlating both on the basis of microstructural as well as petrographic features, like our myrmecite as well as SGR GBM type of dynamic recrystallization.
Yeah, you are correlating all the deformation features. Like the
We are getting in the same thin section, so we are correlating, like unifying all those things.
Because whatever you are dealing is the granite, right? Granitoids. Maybe converted from the granite. So if some myrmecite may be present in the parent rock, then it can be present as a relic. But then how you can differentiate these things? So that's why I'm.
Yes. That's what I told, that these high temperatures are preserved at only few places as a relic. At most places, these are overprinted by low temperature sinistral strike slip shearing. So where we are getting this high temperature kind of deformation thingy, like SGR GBM type of dynamic recrystallizations, we are also getting chessboard twinning and GBM and deformed MD, all these things. So we are just trying to combine all these features to correlate, this has formed at this depth at this temperature. So that's what I was trying to.
Okay, thank you.
Thank you.
Anupam sir, please.
Yeah. So, first, congratulations for the nice talk.
Thank you, sir.
And a very nice attempt to do this kind of correlation. So I have a few small questions, mostly for my own clarification. First thing is that what kind of rocks you have used for this? I mean, are you using only periodic granulites for this?
No, sir. We have basically used all G1 granite at some places, and G2 granite. In terms of shear zone, all these has been sheared during D2 deformation. So
my question is that are these granites emplaced along the shear zone, or the shear zones are post granite?
Sir, just 840 million year granite intrusion is, and 834 to 778 million year ductile deformation is. I have dated these ductile deformation with the help of monazite geochronology, and in that geochronology I have taken those monazite grains which are formed in those particular foliations. So I have dated those through those monazite grains. We get that, yeah. And these granites has been dated previously by Singh et al. From my lab only, by Singh et al. Through zircon dating. I have dated these shear zones and fabrics through monazite.
That is
So,
right. I have also read the paper by Singh et al. But now the question is, if it is the granites that you have used for this quartz microstructure, then you are interpreting this as the exhumation of granulites, no?
yes.
So these peletic and mafic granulites and the granites, the corresponding granites,
Yes, sir.
were they emplaced at the same depth? What is the guarantee?
No, like emplaced before this shearing.
That is fine.
Yeah.
But the exhumation of granulites is being monitored by the reverse slip or lateral slip of these shear zones, huh?
Yes, sir.
So,
Yes.
But your studies from the granitic rocks, the quartz of the granitic rocks. So
Huh,
how can you
I'll
directly
means-
say
Uh-huh.
that from certain depth the granulites have been exhumed? Because unless you can assure us by scientifically, of course, that these granites were emplaced just
Before shearing.
during or before, just during or after the granulite metamorphism. I am talking about the granulite metamorphism vis-a-vis the shearing.
Okay, sir. Granulites have been formed at 860 million year. During D2 deformation, D1 deformation. So during D2 deformation, our granite at 840 million year emplaced. So before that, what happened in that area? We have G0 granite, G1 granite, G2 granite, granulite. All these things happened before shearing, and our shearing started at 834 million year. So during the shearing, these particular granulites, which has been formed earlier,
no, that is
prior to these structures.
So in that case, do you find any kind of decompression texture in the granulites?
Decompression, melting.
Decompression texture, decompression, and kind of any kind of mineral reaction which indicates that there is a decompression, steep decompression, because you are exhuming the granulites along some plane.
Yes, sir.
So obviously you expect some decompression microstructure.
Yes, sir. Yes, sir. Like garnet is converting into biotite, like that. Yeah, we have found those evidences, and we have
that decompression you are correlating with this D2 deformation when they are exhumed.
Yes, sir. Yes, sir.
Okay.
That this has been exhumed from deeper crustal level to lower crustal level, like that.
Okay, then your decompression, that will be a very good thing for your PTT path if you construct, because then your prograde metamorphism has occurred to 860 or whatever, and then your decompression, whether it is ITD or not, I do not know, but the decompression and the subsequent cooling of the granulites will take place at your 834 or whatever. So that kind of construction can be done if you can show this directly correlatable with the shearing and exhumation. That is one of my questions. Then another one, small question, is that you are showing even when you are showing the lateral slips, the low-grade myelonites, there also you are showing a change of mechanism from
GBM to BLG.
Sorry, not but BLG to SGR, bulging to subgrade rotation. You have shown in your final conclusion. My question is that, okay, during exhumation, I understand that this GBM can be overprinted by SGR because that is a lower temperature pressure phenomena. But why in a lateral slip there will be a change in mechanism of from high temperature low temperature to higher temperature mechanism?
Sir, should I answer?
Yes.
Okay, thank you, sir, for pointing out those PT path calculation. Nice suggestion. I will try to accommodate in future studies. I haven't done metamorphic part in that particular area, so I will try to take your suggestion and will do these things in future. So our next question was how these particular dynamically recrystallized mechanism is facilitating these flows from vertical to horizontal, how this flow has been shifted.
No. My question was that you are showing that during your reverse movement, the thrust movement and exhumation, you are showing in many of the shear zones that there is a transition from
SGR to
SGR, GBM to SGR. Because so the SGR is overprinting the GBM. We understand that GBM is a higher temperature mechanism, so it is being overprinted by a lower temperature pressure mechanism because it has exhumed. But in another one, you are showing that within the laterally shifting strike slip motion shear zone, there is a change mechanism of BGA to subtend rotation. So with an increase of temperature, that should happen. But with the lateral shearing, there should not be an increase in temperature or pressure. Then what is the explanation?
Sir, it is around I have shown in with the calculation of paleopiezometry and temperature. I have shown in the slides that from around 18 kilometer we are getting SGR type of recrystallization, and above that at 22 kilometer we are getting GBM recrystallization, 18 SGR. Then around 16 kilometer it is converting into BLG to SGR, or most dominantly BLG type of dynamic recrystallization mechanism. So what is happening here at lower levels, we have low differential flow stress, and in that particular part we have high the grain size is what I was saying. We have large grain sizes, and these are flowing in a vertical direction. As the paleopiezometry or differential flow stress increases, these grain size decreases and accommodated in a lateral flow because as I shown in strength profile, it was in a thrusting mode. For thrusting mode above the brittle ductile transition zone, it needs differential flow stress around 230 MPa.
No, but Sudheer, just a minute. You are, according to your own calculation, you have not crossed the threshold of brittle ductile transition for a quartz of rock because you are coming only up to 15 kilometer depth, where quartz will be in any case very much ductile. So there you are showing that you are having bulging decrystallization. Then it is being overprinted in a lateral movement. It is being overprinted by subgrain rotation, which you are actually finding at 18 kilometer depth. So is there any mechanism by which in a strike slip shear zone your depth changes from say 15 to 18 or 20? That is my question.
Yes, sir. It changes, and in the field also be like what we can say. We find different kind of I haven't done metamorphic type of study, but we can see there are some green cyst facies of myelonite, grade of myelonites, then amphibolite grade of myelonites, then granulite grade of myelonites. So from the field or metamorphism, we can also see that these are changing, but sorry, I think I cannot.
ठीक है, इसके बारे में सोचना, क्योंकि lateral movement जब हो रहा है तो depth का change नहीं होना चाहिए ना. In that case, you should not expect the mechanism to change from lower temperature to higher temperature. Usually, okay. So अगर होता है तो कुछ तो होगा उसका explanation that you can basically explain, you and your colleagues who have worked there. We do not know. So this was just a kind of slight inconsistency that I pointed out for your future pondering. Okay.
Thank you, sir.
Thank you.
Trideep, I have a question. I think Trideep, yeah, go ahead.
Yes. Thank you, Sudheer. Thank you for a nice presentation, and it's a very good work. I have two small queries. The first one is, I mean, you have collected the sample from the shear zone only, right?
Yes.
I mean, have you ventured any sample, I mean, not from the shear zone, I mean, away from the shear zone, but from the granite? I mean, have you checked any sample?
No, I have collected these samples from D2 shear zones only.
Only from the shear
Only
zone?
shear zones. Yes, sir.
Okay. And my second query is, have you done any AMS study, anisotropy of magnetic susceptibility for the granite or the shear zone?
No, sir.
No, although you have not presented, I mean, just for my query, I'm asking. I mean,
yes,
have you
I haven't tried. We haven't tried AMS study in the Ambaji area till now.
Okay, thank you, Sudheer.
Yes,
thank you.
I think Pradeep, Sudhir was showing some beautiful stretching lineations. So if you have a distinct stretching lineation like that, and then definitely, obviously, MS is definitely useful. But at times we can also avoid it. I think with in case we are having those kind of stretching lineations. So
Sandeep, I completely agree with you. Even if the rock shows prominent stretching lineations or foliation, whatever, the AMS can be used. I mean, it can give very useful information. So just I'm asking.
No, it's okay. Yeah. No, I was just thinking that probably why he has not done. I think.
No, but you can venture in future.
Definitely.
But JD, Sandeep is right. If you can see the lineation directly, then why do you need magnetic lineation?
Yeah, sir. I mean, there is one paper, Fede et al. I think 2014, and they have used extensive AMS on the shear zone, and they have concluded many things. Okay, so I think what Sudheer has done, I mean, if he does this AMS analysis,
he can explore more. Obviously,
he can explore more. I don't know. I mean, what he will receive, but my hunch is that he may get some extra information. So
right.
That's my intuitions.
Yeah. No, I was just looking for a probable answer from his part. Actually, I think
that's fine. That's fine.
That possibly
anyway,
why
Sudheer, that's a nice work.
Yeah.
Thank you, sir.
Professor Dilip Shah, I think, want to comment. Yeah. So.
Well, first of all, let me thank Dr. Sudheer Tiwari for sharing with us his elaborate work on dynamic recrystallization of quartz from Ambaji Granulite belt. If I can just go back to what Dr. Vikramaditya Singh commented on, I think Pushpendu also commented on that. Why? Say, for example, you showed some samples where you said that you have stretched feldspar as well, right?
Yes.
So these are from the shear zone itself.
High temperature shear zones.
So it would have been nice to see whether there is any recrystallization in there. What kind of feldspars are they? You showed one plagioclase,
basically K feldspar.
But you also showed some plagioclase deformation.
Yes, sir. There are plagioclase also and K feldspar, both are.
So do you see actual recrystallization in feldspar?
Yes, sir. In thin sections, I have seen dynamic recrystallization in feldspars also.
I see.
In high temperature shear zones.
I was just wondering because, I mean, if I have heard correctly, I may be wrong. You said that even if you try the feldspars dynamically recrystallized grain size, you would get similar sort of differential stress estimates. But that would depend on, you see, whether you are assuming uniform strain rate or uniform stress rate. You see, if you are assuming uniform strain rate, then feldspar and quartz will be supporting differential stresses which are different. So that if you are planning to do any feldspar piezometry in the high grade rocks, of course, I mean, I think you should keep this in mind. See,
Yes, sir. In future, I will do.
Now, coming back to the question of exhumation, I was really not very convinced that the shear zones have only the shear zones are the causes of exhumation of high-grade rocks. Because you see, if you go back to your map, you don't have to show now. I remember, correct me if I am wrong, that you have mafic granulites on either side of the shear zone, your green patches, if I recall correctly, right?
Mhm.
So on either side of your shear zone, whether these are deep slip shear zones or these are strike slip shear zones, you have high grade granulites. So they have been exhumed from deeper levels by some other mechanism, you know. And one may argue that even your shear zone was exhumed in toto with those things. This is another point. I think if you are planning to do future work, then you should keep that in mind. One other point that perhaps you should keep in mind is that your granites, as Anupam was trying to hinting at, that the granites may not necessarily have been emplaced in the granulite depth. I mean, depth. They may have been emplaced at a shallower depth, you know, and then they were sheared. So we should also try to say kind of put some constraint on at what depth your granites were actually emplaced, first emplaced. So these are the few observations that I would like to make. Otherwise, I mean, I'm happy that you shared your work with us, and all the best for your future work. Thank you, Tiwari.
Thank you, sir, for nice suggestions. I will take care in future all those points.
Sudhir, I think Srideep has another query.
Yes.
No, Sandeep.
Okay. Yeah.
Sudhir, just one suggestion. I mean, what Pushpenduda told, I mean, he rightly pointed out about the feldspar piezometry. One suggestion, you can see, I mean, if you have not seen, Z and Lee tectonophysics paper, I mean, 2021. They have done this feldspar piezometry recently, I mean, 2021, Z and Lee.
Yeah, can I add something? Can I add something?
Please.
Yeah, so recently one paper published in Journal of Structural Geology by Speciale, and I think you can go through this paper, and actually they made the thing with a combined quartz feldspar piezometer, and
Pushpendu, I think they have worked on mineral pairs.
Yes. They have worked on mineral pairs, and this piezometer to some extent differ from the piezometer what we are getting from Stephen Talley. So right. If you calculate the flow stress from this plot, this will be different from the flow stress you are getting from the quartz.
That may be more accurate, as our crust more or less is granitic, so quartz and feldspar combined may be good for calculation
of
geological properties.
Yeah, they have worked on mineral pairs like quartz, feldspar, then olivine orthopyroxene, like that they have used, as far as I remember. Sudhir, please go to your chat box. There are a few queries. You'll be able to see over there.
Okay. There are few shear sense indicators which are showing an opposite sense of shear than suggested of your slide. Okay. So there may these are not opposite shear sense. Basically, these are backward rotated. There may be backward rotated grains, because during we have both simple shear and pure shear. So during simple shear, grain rotates forward, and during pure shear, grain may rotate forward or backward depending on its initial position, like this. Then it will rotate in this direction. If it is in this direction, if pure shear component is this, it will rotate in this direction. If your shearing, your shearing is going in this particular direction. Overall, your foliations, RESC fabric will show in the same direction in which direction your shearing is happening, but your grains may be rotated forward or backward in response to that pure shear. Like it may be both. So yeah, it may be there. There may be grains which are showing backward rotation. There may be grains which are showing forward rotation. But overall, shear zone is showing a sinistral northwest or top to northwest sense of shearing.
So you are suggesting not to rely only on the
only on
grains.
grains we cannot rely. We have to see different microstructures, suppository fabric and all those things.
I want to know that. Second question again from him.
Yes, sir.
One interruption, Sudheer.
Yes, sir.
If you now say that these shear zones are possibly general shear zones, like combination of simple shear and pure shear, then there will be another problem coming. Then you are interpreting that the stretching lineations are indicating the movement, shear movement direction, but in general shear zone it is not necessary.
Yes, sir. But it depends on how much percent of pure shear, because in nature it is not like 100% pure shear.
That is true, but have you calculated the vorticity number?
Yes, sir. I have calculated and published in structural geology. So I have calculated that high temperature, these particular shear zones are showing more of a pure shear kind of component, and these low temperature shear zones are dominated by more of a towards simple shear, kind of like 80% simple shear, 20% pure shear kind of thing, like that. So it is generally non-coaxial during exhumation, but yeah, our pure shear and simple shear varies during the exhumation process.
Okay.
Yeah, and Sudhir, there are two more questions, I think.
Yes.
You can look at the chat.
How the strain rate have been measured? So strain rate I have been measured with the help of grain size analysis. With the help of grain size analysis, first we have calculated that paleopiezometry sigma, and that paleopiezometry we have used in second formula, which is given by Patterson et al. In that and also likely range of deformation temperature, which is given by Stephenopoulos et al. 2003, that particular graph. So by combining all these things, we have put those values in the formula. So by putting those things in the formula, you can calculate strain rates. So next question is,
can we link this myelinite rock with metamorphic grade? If possible, how can we determine metamorphic grade of any myelinite?
Metamorphic grade you can determine with the presence of minerals in those particular myelonites. Suppose if you are getting these kind of minerals in greensious species, what kind of minerals you are getting in these granitic myelonites? Biotite, quartz, and feldspar, all those things. In high grade metamorphic myelonite, what kind of minerals you were expecting? Suppose garnet, grain, and all those things, spinel, cordierite. You may find all those other minerals in high grade metamorphic rocks, which are not overprinted by these things. And yeah, you can correlate these things with metamorphism, but as I am not no metamorphic expert, so I can't go in the in that particular direction. Yes.
Okay, Pushpendu have another query, I think.
Hello.
Yeah.
Hello.
Yeah. So you are calculating flow stress from steep and tallies, okay, and then you are calculating the strain rate from the Patterson, what he did experimentally, okay. So is it rational to link these two kind of experiments?
Yeah, many many researchers have previously done this kind of study. So I have followed them because, yeah.
No. What is your logic to link? Because the experimental setup, what Stephen Tully's have been done. So this setup is bit different from what the Patterson did. Okay, so I'm saying if the deformation conditions of both the experiments are different, so and you are linking both the equations derived from two different experiments, and you are using the empirical constants from two different experiments. So what is your logic to link?
Basically, I was thinking that, yeah, they have done experimental study for the same thing, like for quartz dynamic, to study the dynamic recrystallization of quartz. And for a particular pressure temperature, we can say that at that particular, if we apply that thing, paleopiezometry or temperature, then that particular GBM, suppose GBM will develop at that particular high temperature range only. So that's why we have chosen, like, both have different constant, but for the same minerals they are doing experiments, and nearby the values they will get for the same mineral will be around the same. Suppose for high temperature he will also get GBM and like that. So that's why I have applied these two things.
Okay. I think we should think about this thing.
Yeah.
Okay.
Hello. Yeah. Okay, so if there are no more queries, I'll like to invite Professor Mandal for his comments, final comments before we.
Hello, Sandeep. I think we have a very senior person, Professor Sumit Kumar Ray.
Acha, sir is here. Okay. Yeah. Now I can see.
He has huge experience while working in the research team. So his comments should be very much fruitful for students.
Right, sir. Yeah.
Okay, thank you, Nibir Mandal, for putting me into this very difficult situation, because so many people, I have never worked on these macro structures or paleopiezometric determinations, but I was following the discussions, very important and very pertinent points emerged. One was that Professor Dilip Shah pointed out that side by side you have massive granulites as well as the granulites which are within the shear zones, showing the features that you have studied. So one thing is that this needs to be investigated, because in that case the shearing is not the only mechanism for exhumation. Number two, the other point that repeatedly emerged was that use of feldspars for the paleopiezometric determinations you have done only with the quartz grains. So that was the other suggestions, and some very useful suggestions emerged on this use of the pressure temperature path for further addition, further take the studies to other level. I think Professor Mandal, Trideep suggested that AMS studies may be taken up for further strengthening your observations. So these are the only things I could get, and thank you very much, Sudheer, for this doing this study, taking up this challenging study entirely on microstructures, of course backed by some field observations, of course, the shear zones, their orientation as key to the main northeast, southwest orientation of the Delhi Aravalli fold belt. You have a northwest, southeast orientation of the shear zones you have studied. So I congratulate Vikramaditya. Professor Vikramaditya Singh also pointed out that the myelonites and the questions emerged on whether the when was the relative timing of transformation of the granites to granulites vis-a-vis their exhumation. So granites were when they were transformed, that they were exhumed as granulites. So when were the granites transformed to granites? I think that was discussed in detail by our Chattopadhyay from Delhi University. So these are the some points which I have I could get, and I think these are very good suggestions I had emerged, and you have taken up. You have done a very interesting work in a domain otherwise studied very well, but not from this point of view, from this angle. So these are the points. Now I would say that Nibir, now you better your comments we would like to hear. Thank you very much, Sudheer, for your presentation.
Thank you, sir. Nice suggestions.
Now, Shubhida, you have already narrated what are required for Sudheer to in his future work. I have only one comment, Sudheer, that while applying any theory or model in your study, you have to be very careful about the basic premises in which a law or theory or model works. For example, when you are applying quartz as a piezometer or recrystallization based on recrystallization modes, you have to look at when these equations, empirical equations that have been generated out of experiments could be applicable, because this is applicable essentially a single phase system. This doesn't work when you are taking a multi-phase system the way you are. Some people have asked these questions, raised these questions, like quartz feldspar. Because in that case, when you are mixing two phases, let's say quartz and feldspar, they have completely different properties. So the internal stresses, strain rate would be extremely heterogeneous. So the value that you are getting will not yield the real value of this system. So this is, I gave one example. So you are young, you are going to take your career much ahead. So you have to be very careful with the basic premises of theory and law or model you are inducting in your studies, right? Otherwise, I enjoyed your talk. Thank you, Sudheer.
Thank you, sir. Sir, I have taken only for this analysis quartz-rich zones from those particular shear zone. Although I will agree that yeah, different phases should has been accommodated for the further confirmation.
No, similarly, Sudheer, when you are talking about thrust, strike slip motion, all these models must comply with the tectonic stress field that should prevail in your convergence setting, right?
Mm-hmm.
And similarly, your terrain has undergone a number of deformation episodes. So the initial orientation might have been quite modified. So all these issues you must take into account, not only here, in your future, whenever you are planning for a work. So the fundamental, the concepts that have to be, concretized before you take up any kind of problem, right? Okay, thank you again, Sudheer.
Thank you, sir, for your suggestions.
Thank you all for your comments. Shantanu is here, I think. Okay, so I think there are no more queries. So thank you all for participating in this monthly lecture, and I'd like to again thank Dr. Sudheer Tiwari for his detailed lecture, and we'd like to hear more from you in the upcoming RDS.
Sure.
I'm sorry. So
all to Shantanu. Yeah.
So Shantanu, you meant me Shantanu or Shantanu Bose Shantanu?
No, Shantanu Bose. I usually We'll call him
then it's
Shantanu
fine.
sir.
Okay. So so you asked me, or?
Yeah.
Okay, I mean, I heard, but I mean, I had some network issues. But it's a good talk. I read through this paper. It's all right. I mean, just to say that there is a machine in place now in my laboratory where you can deform the rocks at high pressure and temperature. So bring the rocks and get the real stress. Not an actual strain rate, but you can get it.
Thank you, sir.
So that is there. I'll probably give a talk soon, and we'll see what we can do. Thank you very much. It was a nice talk.
Thank you, sir.
Let's. And before I will close the session, I request you all to register as quick as possible for the next RDS VII.
Yes, tickets need to be booked also.
So, thank you all for your virtual presence. Thank you, Sudheer.
Thank you, everyone.
Goodbye.
Bye.
Bye, sir.